Hello, can anybody hear me? Oh, okay, good. You guys can hear me. Give me just a second. I think I figured out how to share screen with you. So I am just pulling up the slides. You guys can all hear me. I can't hear myself. So you guys can all hear me talking right now. Oops. Okay, I am just pulling up the beginning of the slides. Oops. Okay, can you guys all see the slides? Can you view them? Okay, will you let me know in the chat? Okay, I see somebody. It looks like you guys can view the slides. Button my shirt. Okay, so I don't know if this is a better format because I can't really hear anything, but at least at least you guys can see the slides a little bit better. I can't hear anything. I don't know what it sounds like to you guys. I don't know if you guys can hear like stuff in the background or what, but I'm just gonna go through the slides and the lecture for today, and I guess you guys will have to give me some feedback on if this format works better than the you know what, let me hang on, I'll be right back. Okay, I want to check on my phone if I can view this. So, okay, I think I can see what you guys see, so I'm going to try and adjust the slide a little more. So now I can see the chat and I can see everything else. I can't hear anything, so I am going to get started with the slides. Please type in the chat and let me know if you guys have trouble hearing me. I have like a fan on, so I don't know if any of that will affect what you guys can and can't hear. And then I'm going to go through the slides. I can't hear anything. I can't hear myself. So just type in the chat if you guys have any questions or stuff like that, and we'll see how this goes. Okay? So today, here we are again. We're going to talk about conventional flow, electron flow, electromotive force, and current electricity. And current carrying capacity of wires, and we'll also talk about calculating voltage drops. Okay, so we'll start with conventional flow, conventional and electron flow. Okay, so we have what is conventional current? Before the discovery of the electron, scientists assumed that current was due to positively charged particles moving from the positive terminal around a circuit to the negative terminal. So there's a diagram of that here. You have your 2-volt little battery, and those arrows are showing you that the current is moving from the positive terminal to the negative terminal. That's in conventional flow. This way of expressing the direction of current is called conventional current. It is now known that charge is carried by electrons flowing from the negative terminal to the positive terminal. This is called electron flow. So in the early days, it was actually Benjamin Franklin that came up with conventional flow, who assumed that current flows from the positive terminal to negative, but upon further investigation, it's been found that it actually travels the other way. So today, both conventional current and electron flow can be used to represent the direction of current. And this just also tells you that conventional flow and electron flow are used in industry wiring schematics and diagrams. You will see in your textbooks and other information that they use both electron flow and conventional flow. So a little bit about conventional flow. First developed by Benjamin Franklin, it was thought that current flowed from a positive source to a negative source, concluding that electrons would seek an area with a lack of an abundance of charge. Meaning in the negative force, if it flowed from the positive force to the negative force, then it was seeking an area that had a lack of abundance of charge. And we have a couple of diagrams that show us the conventional flow. So the first one on the left shows us, it's flowing from the positive end of the battery to the negative end. And the other diagram also shows a little light in the circuit there, but just showing the direction of flow of electrons in conventional flow. Electron flow, an abundance of electrons flow out of the negative source to an area that lacks electrons or the positive source. So electron flow is what they found later, and but you'll still see both electron and conventional flow used. Electron charge moves from the negative surplus side of the battery to the position deficiency side. It's just a more complicated way of saying the same thing, really. And then we have the notation of positive and negative. So our positive notation means an abundance of charge. That's what the plus stands for. And our negative notation stands for a lack of charge. Sorry. Okay. Another diagram here, the direction of flow from our batteries just shows you kind of a comparison of conventional flow and electron flow. And we have electromotive force. So electromotive force, it also is abbreviated by EMF, is the push or pressure felt in a conductor that ultimately moves the electrons in a flow. We'll talk a little bit about current, electromotive force, and voltage. What's the difference between all of them? Voltage is considered the value between 2 points. Current is the flow of electrons. EMF has the symbol, if you're measuring EMF, the symbol for that would be a capital E. And potential difference is needed to make electrons flow from one position to another. EMF. If we measure the EMF between 2 points on a 12 or 24 volt battery, the EMF would be 12 or 24, depending on which battery. Capital E stands for EMF. This means that between those 2 points, there is an available EMF of 12 or 24 volts to push current through a circuit. So that's a little description of EMF. So voltage versus EMF, are they one and the same? Are they the same thing? I know that that's your question right now, but they are not. They are very close, but no, they are not the same thing. Voltage is a word used to describe electrical potential difference. EMF is a voltage provided by a power source such as a battery. Okay, so voltage makes electrons flow while EMF maintains potential differences. Volts push current around an electric circuit. Voltage from a power source behaves like a push start. Voltage begins pushing electrons around to induce electrical current. So voltage is like the push start for the current that's going to be moving. More about voltage, it's a term that describes the amount of work it takes to move a unit of charge, which is +1 coulomb, from points A to B or B to A, whichever direction it's going. A voltmeter is the tool that is used to measure voltage. A battery can provide a voltage between the two terminal endpoints. So the two terminal ends of a battery are going to give you your voltage reading for that battery. The positive side has a higher potential and the negative side has a lower potential. Voltage also means potential energy, the potential to do work. It has the potential to move current and provide energy. If that potential is not given power or push by the EMF of a power source, such as a battery, then the voltage will never provide any energy. So voltage is only a potential energy unless it has a electromotive force, such as a power source, like a battery, stuff like that. Okay? So I'm going to say that again. Voltage has the potential to move current and provide energy. It only has the potential. But if that potential is not given power, or we could call it a push, by the EMF, the electromotive force of a power source, such as a battery, then the voltage will never provide any energy. Okay? So we also have counter EMF. When we're working with electromotive force, we also have to account for counter EMF, which is EMF that is residual, that works in the opposite direction of our electric motive force. So this video gives you a good description of how that works.
EMF, or electromotive force, refers to the voltage created by a battery or by a changing magnetic field. Counter EMF, also called back EMF, is a related phenomenon that we will illustrate in this animation. Here is a simple circuit featuring a battery, a knife switch, and a light bulb. This circuit also contains a wire coil that serves as an inductor. Inductors store energy in the form of magnetic fields that are generated around them when a current passes through them. They are called inductors because they induce a voltage in their coils when that magnetic field changes. We will see this in a minute. The elements in this animation are not represented to scale, and the action we will show in super slow motion actually takes place in the blink of an eye. But this animation is helpful for illustrating how back EMF works. When we power this circuit, the electrons in the current create a magnetic field around the wire as they move through it, as shown by these blue arrows. If the wire is formed into a coil, like this inductor, the magnetic field lines converge in the center. They gradually build up to a maximum magnetic field that is much stronger than the one around the straight length of the wire. Let's watch this again, but this time we'll pay closer attention to what's happening in the wire conductor. In this parallel circuit, the current can travel either through the inductor or through the light bulb. When the current reaches this junction, it splits and flows to both the inductor and to the light bulb. At first, the current flows much more strongly towards the light bulb. This happens because as the magnetic field in the inductor grows, it induces its own voltage through Faraday's law. This is called electromagnetic induction. So the inductor here is creating a back EMF represented by this yellow arrow. Back EMF always opposes the change that created it. So in this instance, the back EMF is opposing the change created by turning on the circuit. It opposes the current. The result, as you can see, is that the back EMF effectively diverts the current away from the inductor and toward the light bulb. This causes the bulb to light up, but only briefly. Once the magnetic field around the inductor reaches its maximum field, the back EMF fades, and the current now favors the path through the inductor because the bulb creates some resistance to the current. The same phenomenon occurs when the magnetic field is shrinking, which happens when we open the switch and stop current flow from the battery. Once again, the back EMF opposes the change that created it. In this case, the change is the cessation of current. So, opposing this change, the back EMF wants to maintain the current, which flows once again to the bulb, causing it to flash before it fades away altogether.
Okay, so I hope that helps you understand EMF, counter EMF, back EMF a little bit better. There's more information about it in your book. Okay, so we're going to move on. We're going to move on to current. So we've talked a little bit about current electricity already. I think we went over Ohm's law, how to find current in a circuit. So we're going to get a little more in-depth with that. Current is a measurement of a rate at which a charge flows through a conductor or a point in space. We have an electrical formula to figure out current. So remember, the symbol for current is I. Not to be confused with the unit of measurement for current is amps, capital A. So the greater amount of charge moving through a conductor in a given amount of time is what makes current. And this is our electrical formula for current. We have current equals charge over time, where I means current measured in amps, capital A. We have capital Q means charge measured in coulombs, coulombs being a capital C. And we have time, a T, meeting time. Okay, so all of these, this key over here can be plugged into what this formula means. So we have current equals our charge measured in coulombs over time. And what that looks like is, well, what's a coulomb? What is a coulomb? I don't think I'm saying it right. It's coulomb or coulomb, one of those, but I say coulomb. A unit of electric charge, that's what a coulomb is. The amount of electric charge that is transported by an electric current at 1 amp per second. So that also means 1 amp traveling per second delivers 1 coulomb of charge. Okay, so in mathematician words, a coulomb can be broken down into this equation or formula. So we have 1 amp. Well, what is the measurement of 1 amp? So 1 amp in electrons is 6.24 times 10 to the 18th power, which is actually, I think it's like 6.24 billion, basically, electrons. And we have that many electrons flowing through a certain point for 1 second, and that equals 1 amp. That is what 1 amp is broken down into. So what's 1 coulomb? 1 coulomb, we said, is the charge that's carried on 1 amp, right? And that's per second. So if we want to know what a coulomb is, we have in 1 amp is equal to 1 coulomb flowing for every 1 second. Okay, so this gets broken down pretty far. We're not really going to be measuring anything in coulombs. This is just the background information on current, how current's measured, how amps are broken down, which is basically, your basics for basic electricity. Current and electrical formula notation. So you should be able to, from the previous slides, you should be able to know what this equation might stand for. And it reads 1 amp equals 1 coulomb over 1 second. Remember that equation that we had a couple of slides ago? Okay, so we have current equals charge over time, right? So if our current is 1 amp, that would equal the charge, which is the charge on our 1 current is 1 coulomb over the time. And we deliver 1 coulomb for every 1 second. That gives us 1 amp. Okay, so that's all of those factors plugged into that equation. And that's what it looks like. 1 amp equals 1 coulomb over 1 second, or per second. Okay, so we also have direct current. Direct current being DC, and that means when current flows in one direction. We have alternating current, AC, a form of current that periodically oscillates back and forth in a circuit. And we will get more into the details of AC and DC and circuits and stuff like that later in the course. Sorry, my dog keeps chewing on stuff. He's like never allowed in this room, so now that I'm doing lecture, he's trying to chew on everything. And we're also going to talk about current carrying capacity of wires. Okay, so I have this,
After getting stuck on a math problem for hours, my mind was
After
toast.
getting stuck on a math problem for hours,
It was time to try
my
Chegg
mind
Study.
was toast.
First, I used step-by-step
It was
solutions
time to try
that made
Chegg
my
Study.
tricky textbook questions super easy to understand. And when I needed extra help, I
oh yeah, there is no sound for that video. You just have to read it.
Hi, it's Sam Barker here from the Motley Fool. Behind me is Landmark.
Was that viewable? Could you guys see that video? It doesn't have any sound. It's just some slides on electrical carrying capacity for wires. Okay, well, you guys can go back and view that video as needed. There's also more information in your textbook about the current carrying capacity of wires and how those work. Okay, so we're also going to go through calculating voltage drops today. So calculating voltage drops in a circuit, current will flow from high potential to lower potential. When that current flows through a resistor, we can observe the voltage between two ends. The difference in, oops, I just dropped something. The difference in voltage, where was I? When that current flows through a resistor, we can observe the voltage between two ends. The difference in voltage at those 2 points is called a voltage drop. Basic voltage drop law. So we have our voltage drop equals current times resistance. That's our formula for calculating voltage drop. In this formula, we have I, which, like we've said before, stands for current measured in amps, capital A. We have resistance of the wires, that's what we're measuring, measured in ohms, with the ohm symbol. What causes voltage drops? We have 4 basic causes. Material of the wire can cause voltage drops depending on what that wire is made out of, what wire has been chosen to use. Wire size, wire length, and amount of current running through the wire. Those are all causes for voltage drops. Kirchhoff's law. So in Kirchhoff's law, for any junction in an electrical circuit, the sum of the currents flowing into the junction is going to be equal to the currents flowing out of the same junction. So what that means, a junction meaning any point that meets some resistance. So for these, for this subject, we're going to be talking about resistors, and that gives us a resistance in our circuit. So for any junction in an electrical circuit, the sum of the currents, so the total of adding the currents flowing in that junction, into that junction, meaning going right into that resistor or whatever is resisting that electrical current, is going to be equal to the currents flowing out of the same junction, so flowing out of the other side of whatever's resisting it. You should still always have the same current. And this is a good video on practicing voltage drops. This one does have sound, so you'll be able to hear it.
Big thanks to you guys at home.
In this video, we're going to talk about how to calculate the voltage drop across a resistor. So let's draw a circuit. So this is the electrical symbol for battery, and that is for a resistor. Now this is the positive terminal of the battery, and here we have the negative terminal of the battery. Now we're going to use a 20-volt battery. This is going to be R1, and this is going to be R2. Let's give R1 a value of 2 ohms, and R2 is going to be 3 ohms. What is the voltage drop across R1? And what is the voltage drop across R2? So what do you think we can do to find the answer? In order to calculate the voltage drop across a resistor, you need to know the resistance and the current flowing through the resistor. So first, we need to calculate the current flowing in the circuit. So how can we do that? Well, first we need to know what type of circuit we have. And this is a series circuit. The reason why it's called a series circuit is because the current has only one path to flow through these resistors. So these resistors are in series. Now, in a parallel circuit, the current can flow in multiple directions. When there's multiple paths for the current to flow, then you have a parallel circuit. But in a series circuit, there's only one path for the current to flow. Now, the current that we're dealing with is conventional current, where it flows from the positive terminal to the negative terminal. But keep in mind that electrons, they flow in the opposite direction, from the negative terminal of the battery to the positive terminal. Now, before we can calculate the current in a circuit, we need to determine the total resistance. For resistors in series, the total resistance is the sum of all the resistors. So in this example, it's simply 2 plus 3, which is 5 ohms. So that's the total resistance of this circuit. Now, to calculate the current flowing in a circuit, we're going to use the voltage of the battery and the current flowing in this circuit times the total resistance. So this comes from Ohm's law, V equals IR. So the voltage of the battery is 20, the total resistance is 5, 20 divided by 5 is 4. So the current flowing in the circuit is 4 amps. Now once we have the current, we can now calculate the voltage drop across each resistor. Now we're going to use Ohm's law again, V equals IR. But the voltage across resistor 2 is going to be the current that's flowing in the circuit times resistor 2. So we have a current of 4 amps times a resistance of 3 ohms. So that gives us a voltage drop of 12. Now V1 is going to be I times R1. So that's a current of 4 amps times a resistance of 2 ohms, which is 8 volts. So let's talk about what this means. If you were to take a voltmeter and connect it across R1, if you do it properly, you're going to get a voltage of 8 volts. If you do so across R2, you're going to get a voltage of 12 volts. Notice that the sum of the voltage drops in this circuit is equivalent to the voltage of the battery. And it should be that way according to Kirchhoff's voltage law, which states that the sum of the voltages around a closed loop must add to 0. Now, the battery delivers energy to the circuit, so we're going to give it a positive voltage. And the resistors, they take away energy, they consume energy from the circuit, so we'll give it a negative voltage. Thus, they're called voltage drops. So if you add positive 20 with negative 12 and negative 8, you're going to get 0. So that's how you can calculate the voltage drop across a resistor in a circuit like this. But for the sake of practice, let's try another example. So this time there's going to be 3 resistors instead of 2. So we're going to call this R1, R2, and R3. Now the voltage of the battery is going to be 36 volts in this case. And R1 is going to have a value of 5 ohms. R2 is going to be 4 ohms. R3 is going to be 3 ohms. So go ahead and take a minute and...
After 30 days, I could not believe my before and after picture. I literally rolled back the hands of time 10 years. When I first saw this product, I thought it looked kind of crazy. Didn't really understand what the benefit.
Work on this example. Calculate the voltage drop across each resistor. Feel free to pause the video to try this problem. So let's begin by calculating the total resistance. So R1 plus R2 plus R3. So that's going to be 5 plus 4 plus 3. 5 plus 4 is 9. 9 plus 3 is 12. So the total resistance in this circuit is 12 ohms. Step 2 is to calculate the current in a circuit. So because it's only one path for the current to flow, all 3 of these resistors are in series. The current is going to be the voltage of the battery divided by the total resistance of all the resistors in series. So the voltage is 36 volts, the total resistance is 12 ohms. So 36 divided by 12, that's going to give us a current of 3 amps. So now that we have the current in the circuit, we can now calculate the voltage drop across each resistor. So let's start with V1. V1 is going to be the current times R1. So that's a current of 3 amps times a resistance of 5 ohms. So that gives us a voltage drop of 15 volts. Now let's move on to V2. The voltage drop across R2 is going to be I times R2. So that's a current of 3 amps times 4 ohms. So that gives us a voltage of 12 volts. And now to calculate the voltage drop across R3, it's going to be I times R3. So 3 times a resistance of 3, which is going to give us 9 volts. So now let's add these 3 numbers, 15, 12, and 9. So 15 plus 12, that's 27. 27 plus 9 is 36. And that's a quick way to tell if you perform this problem correctly. So these are the voltage drops of each resistor. That's how you can find them. Now let's work on a different type of problem. So let's say we have these 2 resistors and 3 points of interest. We're going to call this point A, point B, and point C. And let's say R1 has a resistance of 8 ohms And R2 has a resistance of, let's say, 15 ohms. Now, let's say the potential at point A is 50 volts, and the potential at point B is 10 volts. What is the voltage drop across R2? And what is the electric potential at point C? Feel free to pause the video and try this problem. Now, what do you think is the first thing that we should do? The first thing we need to do is calculate the voltage drop across R1. The voltage drop across R1 is the difference between the electric potential at point A and point B. It's the potential difference between those 2 points. So it's 50 volts minus 10 volts, which is 40 volts. So that is the voltage across R1. Now, in order to calculate the potential difference or the voltage drop across R2, we need to determine the current flowing through R2. Now, because there's only one path for the current to flow through these two resistors are in series. So we need to calculate the current flowing through R1. We'll call it I. So let's use Ohm's law. V is equal to I times R. So V1 is going to be equal to I times R1. V1 is 40. That's the voltage across R1. And R1 is 8. Dividing both sides by 8, the current is going to be 5 amps. So if 5 amps of current flows through R1, then the same amount of current flows through R2. So now we can calculate the voltage across R2. So V2 is going to be equal to I times R2. The current is 5, R2 is 15. 5 times 15 is 75. So that is the voltage drop across R2. It's 75 volts. Now, let's calculate the potential at point C. The current flows from a high electric potential to a low electric potential. So as the current flows from A to B, this tells us that B is lower in potential than A. Now the current flows from B to C, which means that C is at a lower potential than B. Now we have the potential difference between points B and C is 75, and B is higher than C. So C is going to be 10 minus 75, which is negative 65. So that is the electric potential at point C. And that's basically it for this video. So now you know how to calculate the voltage drop across a resistor. So basically, you need to use Ohm's law. V is equal to IR. You need to know the value of the resistance of the resistor, and also you need to know the current flowing through that resistor. If you multiply those two things, you'll get the voltage drop across the resistor. So that's it for this video. Thanks for watching, and don't forget to subscribe.
Good grammar and spelling are...
Okay, so this, I don't even know what you call it, but this guy, he has some really good videos, especially about math problems with basic electricity. When I can't draw on the board, these are probably going to be some of the videos that I'll use. So if you ever look him up and see his videos, you can take those and practice from them. And I want to correct one of the slides because I think I put in Kirchhoff's law of current, and this is, for this lecture, this is actually supposed to be Kirchhoff's law of voltage. So I am going to correct that right now so that you guys can see that. If I can figure out how to get out of here. Yeah. Okay, so it's actually supposed to be for any junction, this isn't working. for any junction in an electrical circuit, the sum of the voltage into the junction is going to be equal to the voltage out of the same junction, which is exactly what he explained in that video. Okay, and you have your way of kind of self-checking in those problems where you can check if the voltage drops, they should add up to what the voltage of whatever your power source is. Okay, so I want you guys to make sure that you note that. This is Kirchhoff's law of voltage. There is a Kirchhoff's law of current that we will get into, but not today. Whoops. Okay, so I'm just going to show you guys that last slide. That was all that I wanted to cover in lecture today. I'm not sure what you guys are getting into in lab, but I know that Mr. Kimball does want you guys to start understanding how to measure and calculate, especially voltage drops. And okay, so just to review what we went through today, we talked about conventional flow, electron flow. Remember, conventional flow was what was discovered first, but not necessarily how electricity operates. But you will see conventional and electron flow both used in diagrams and schematics. Our annotations for our positive and negative terminals and what they mean as far as electrons. We also went through electromotive force and what that means to us, how it's different from voltage, right? Voltage versus electromotive force. Some information about voltage and how it operates, what the difference is. We talked about counter EMF. Take another look at that video if you need to review it because it explains it really well. And we talked a little bit about current electricity and the formulas that go along with that. Remember what a coulomb is and how that relates to current. There's the formula that we plug in the coulomb and the amps and the seconds, and that's how current flows. Our electrical formula notation. Some descriptions of direct and alternating current. And that video about current carrying capacity of wires. That video does not have sound, it's just slides. So that's something that you can read up on. There's also more information in your textbooks that you should be reading. And how to calculate voltage drops. So I would definitely continue practicing some of those problems with calculating voltage drops. There's our basic voltage drop law formula. The things that can cause a voltage drop. And Kirchhoff's law of voltage. We want to have, no matter what how many voltage drops we have or what the resistance is, we should always have an equal amount of what our power source voltage is. We can't end up with more. That wouldn't make any sense. And that video again is a good video for practicing those voltage drop calculations. Okay, so let me see if you guys have any. Okay, do you guys have any questions? The lecture quiz today is going to be available at 6:30. You guys are meeting with Kimball in lab at 6:35 or whatever. So, any slides that you guys need to see again, just go ahead and type in the chat. You can let me know. If not, that's it for today. Don't forget to take the quiz by midnight. And I will see you for lecture on Monday.